So improper integrals let us do some really cool things, right? Integrating across an infinite interval or integrating a function that has an infinite discontinuity. But now that improper integrals are on the table, it means that we have to be a little bit more careful when we talk about integrals, right? Because the notation for an integral, right, a definite integral where we can use fundamental theorem of calculus, is the exact same notation that we use for improper integrals, where we need to break up the domain and do limiting techniques. So for example, if I was trying to calculate the integral from 0 to 3, and the function I've got is dx divided by x minus 1, it's tempting to write my antiderivative formula and do my fundamental theorem of calculus step, and I'll get a number. But this actually is not the value of the integral here. This integral is an improper integral because my function, my integrand, has an infinite discontinuity at x equals 1, which is right in the middle of my domain. So I would need to use techniques of improper integration to evaluate this. And in fact, this integral does not have a defined amount of area. So this is similar to the integral of 1 divided by x that we were looking at last week. So this is undefined. Integral does not exist. So anytime for the rest of this class, and frankly, any time that you're going to be working with integrals, it's important to figure out whether or not the integral you're looking at will be just a regular definite integral, or if it will be an improper integral. Right. So obviously, when we're integrating out to infinity, that kind of gives the game away. But if we're integrating on a finite interval, let's say from a to b, before I can do fundamental theorem of calculus stuff, I need to make sure that my function f of x does not have any infinite discontinuities in there, or if you prefer, it doesn't have any vertical asymptotes in there. If it does, we'll have to use improper integration instead.